Good morning everyone. Myself Shivkumar Karbari, Assistant Professor from AC Department, GNIT. So today let me explain you what do you mean by half-wave rectifier, the working operation of half-wave rectifier, and I will prove you technically why half-wave rectifier cannot be useful for a rectification process. So before going to this topic, what do you mean by half-wave rectifier? Let me tell you what do you mean by a rectifier first. So the rectifier is an electronic device. It's an electronic component which is used to convert alternating current or alternating voltage into pulsating, or you can say that constant DC voltage. What I am telling, it's an electronic device, it's an electronic component which is used for rectification process. Now what do you mean by that rectification? We are converting input AC voltage or AC current into pulsating. Pulsating is an electronics word, it's a technical word. In general, we can call it as a constant DC voltage or constant DC current. And whatever the process, this process is called as rectification. Now, based on the period of conduction, a rectifier has been divided into two types. Those are nothing but half-wave rectifier and full-wave rectifier. Now our prime focus, the topic is half-wave rectifier. Now let me define you what do you mean by half-wave rectifier. Half-wave rectifier, it's a type of rectifier, or you can say it's an electronic device which converts one half of the AC cycle. This is our AC input. What it was doing, it will convert or it will rectify only one half of the AC cycle. Means in this circuit diagram, your diode will be in conduction mode. Diode will conduct only during one half of the AC cycle. As the name itself indicating you, half-wave rectifier, it will convert only one half of the AC cycle into pulsating DC. Now let me explain you the operation, how does it works. So whatever the diagram here it is there, this is the circuit diagram for half-wave rectifier, which consists of a step-down transformer. This coil is nothing but primary coil, and this coil is nothing but secondary coil, and this symbol is nothing but the air gap between transformer, primary and secondary coil. This is the air gap, and here we are providing an input. Our input is alternating current. Alternating means changing AC input, that is of 230 volt and 50 hertz. This is my input, sinusoidal waveform, and that can be given as x of t is equal to Vm sin omega t. That is my function. This is my input. You can say it as an input. That is nothing but x of t is equal to Vm sin omega t, a sinusoidal function. And here Vm is your peak voltage, maximum voltage, and this peak voltage should be far greater than V lambda, where V lambda is nothing but your cut-in voltage. The peak voltage should be far greater than cut-in voltage. Now cut-in voltage, for example, if my diode is germanium, the cut-in voltage is 0.3 volt. If my diode is made up of silicon, my cut-in voltage is 0.72 voltage. This condition should be satisfied. Now let me explain you the operation. The circuit diagram consists of step-down transformer, a diode, a resistor across a diode. Now let us consider two cases. what will happen for positive half cycle? What I am telling, first case is positive half cycle. My input is positive half cycle. If you apply a positive half cycle, what will happen here? Let me explain you that. So if you apply a positive half cycle, here the voltage which will be induced across the secondary, here you will get a positive, and here at this side you will get a negative. What I am telling you, the positive will be applied at the anode of the diode, means anode of the diode will get positive, cathode of the diode will get negative for a positive half cycle. In this condition, when anode is positive, this is anode is connected to positive, cathode is negative, is connected to negative, means your diode will be under forward bias condition. Positive terminal of the battery is connected to anode, negative terminal of the battery is connected to cathode. It means diode is in under forward bias condition. If diode is under forward bias condition, it acts as a closed switch. This will act as a closed switch. It will be in on condition, and it conducts. It means current will flow across diode. Now my input is positive half cycle. Whatever the input is there, that will be available across output. This is my pulsating DC voltage. Now whatever the input is there, that will be available across output. That's why I didn't draw the output. Now what I am telling, for positive half cycle, the input will be appears across output. So I will draw a positive half cycle only for a range 0 to pi. So this is my output. Now my second case is this. What will happen if my input is negative half cycle? If the input is negative second cycle, negative will be applied to anode and positive will be applied to cathode. Negative to the positive, positive to the negative, means diode will be under reverse bias condition. Under reverse bias condition, vice versa of this, diode will act as a open switch. It does not conduct. It will be in off condition, means no current flows through diode, means your output will be 0. For negative half cycle, I will get a 0 output. So here you can mention D is in on condition, and here you can mention D is in off condition. Like this, again my input will become again positive half cycle. Again for positive half cycle, your diode will act as a closed switch. It conducts, current will flow through diode, and whatever the input is there, that will be available across output. My input is positive half cycle, again I will get positive half cycle. Here you can write down D on. So like this, we have converted our alternating voltage into a unidirectional pulsating DC voltage. Our input is bidirectional, positive, negative, but my output is unidirectional. Here you can say the output is in one direction, only in unidirection. So like this, your halfway rectifier will works. Now let me go to explain you why halfway rectifier cannot be useful for rectification process. Technically cannot be useful for rectification process. So we have a term ripple, a term called as ripple factor. Let me erase this. So we have a term that is called as ripple factor. Now what do you mean by this ripple? Means the amount of certain AC will be present in DC. Now we have converted our alternating voltage into direct voltage, but there must be a certain amount of ripple in the sense some amount of AC will be there in DC voltage. Now we don't know how much amount of AC is there, that is we want to calculate. Based on that, we'll say that half-wave rectifier cannot be useful for rectification process. Now let me define you what do you mean by ripple factor. It is defined as the ratio of RMS value of AC component to the DC value of component. It is defined as the ratio of RMS value of AC component to the DC value of component. So this I can write as ripple factor is denoted as tau is equal to VR comma RMS divided by DC means VDC, that is our average voltage. And technically we know that VR comma VRMS is equal to square root of VRMS square minus VDC square. This is the formula, the standard formula for VR comma RMS. Just substitute this value in the above equation. Tau is equal to a square root of VRMS square minus VDC square divided by VDC. And this VDC can be written like this. This can be modified. Tau is equal to square root of VRMS square divided by VDC square minus VDC square divided by VDC square. This can be written as square root of whole square. If you square root square will get cancelled. That I have done there. And finally I will get square root of VRMS square minus VDC square minus 1. This will get cancelled. Now what I am telling, we need to calculate the ripple factor. How much amount of ripple present, how much amount of AC present in DC. Now in order to calculate tau, we should know what is VRMS and what is VDC. First let me go to what do you mean by that root mean square, what do you mean by VRMS, then I will calculate what is VDC. So listen here, VRMS is equal to, it is defined as a square root of a ratio of a square of that function to the time period. VRMS is defined as, I will repeat it, square root of a ratio of square of my function x of t divided by total time period. So here square root of my x of t is, as I have given, x of t is equal to Vm sin omega t. X of t is nothing but Vm sin omega t. So my time period will be 0 to 2 pi. So total period will be 1 by 2 pi, and x of t is nothing but Vm sin omega t whole square divided by total time period is 2 pi, 0 to pi, pi to 2 pi. So this I can write as integration square root of 1 by 2 pi integration from 0 to 2 pi Vm square sin square omega t d omega t, and for only 0 to pi pi to 2 pi, that is our total time period. By simplifying this, square root of 1 Vm square, take Vm square outside, divided by 2 pi, integration of sin square theta is 1 minus cos 2 omega divided by 2 in the range 0 to 2 pi. In the range 0 to 2 pi. If you substitute the values here, you will get Vrms is equal to Vm by 2. In the final, you will get Vrms is equal to Vm by 2. So this we have calculated. We come to know the value of Vrms. Now next task is to calculate VDC. Now let me tell you how you can calculate VDC. VDC is nothing but average voltage over DC voltage. Average voltage over DC voltage. VDC is equal to 1 by 2 pi integration from 0 to pi. My input is Vm sin omega t whole bracket d omega t plus the one more range pi to 2 pi where my output is 0 into d omega t, close the bracket. This I got like this. My output is here, and for this it is 0. For positive half cycle my output is input only. For negative half cycle it is 0. 0 to pi, pi to 2 pi. For this range my output is input only. That is nothing but here 0 to pi Vm sin omega t d omega t plus pi to 2 pi my output is 0. 0 into d omega t, close the bracket. So 1 by 2 pi, take Vm outside, I will get Vm by 2 pi. Integration of sine is minus cos omega t in the range 0 to pi. So we will get Vm by 2 pi into cos pi is nothing but minus 1 and cos 0 is nothing but minus of minus 1, and you will get total, you will get Vm by 2 pi into 2. So 2 will get cancelled. VDC will get Vm by pi. So we got VDC and Vrms value. By substituting VDC and Vrms in the ripple factor, you will come to know how much amount of ripple is there. So let me substitute here. Tau is equal to square root of, my Vrms is Vm by 2. So we will get Vm square by 4 whole divided by VDC is Vm by pi. You will get Vm square by pi square minus 1. So Vm square will get cancelled. You will get square root of pi square by 4 minus 1. That will give to the ripple factor is 1.21. And if you want to calculate the value in terms of percentage, just multiply by 100. You will get tau is equal to 121%. Means from this equation it is clear that 121% of AC value present in DC. How much? 121% of AC is present in DC. That's why half-wave rectifier is cannot be useful for rectification process. It technically cannot be useful for conversion of AC to DC. So this is all about regarding half-wave rectifier. Now let me explain you few terms. What do you mean by efficiency? What do you mean by form factor and ripple factor? So just let me erase this. Let us calculate the efficiency, form factor and ripple factor of half-wave rectifier. So efficiency is defined as It is denoted as eta. It is defined as ratio of output power to the input power. It may be any kind of a system. In order to calculate efficiency of any system, efficiency is defined as the ratio of output power to the input power. Now how will represent power? What is the formula for power? P is equal to V by I. So here I am telling that output power. In the half-wave rectifier my output is DC. I will write it as PDC. And my input power is AC. I will write it as PAC. PDC by PAC. Now you know in general P is equal to V by I. Now I can write it as VDC into IDC. Just write suffix DC here. PDC, it will become VDC, it will become IDC. VDC into IDC. Now AC is nothing but RMS. AC, keep in mind AC voltage is nothing but RMS. So I can write it as VRMS into IRMS. We know the value of VDC, Vm by pi, and we know what do you mean by VRMS, that is Vm by 2. We don't know what do you mean by IDC and IRMS. So let us convert IDC in terms of VDC. We know that I is equal to V by R. IDC is equal to VDC by RL. So let me convert IDC in terms of VDC. VDC into, just use this formula, VDC by RL whole divided by VRMS into VRMS divided by RL. This RL will get cancelled. You will get finally eta is equal to VDC square divided by VRMS square. We know that VDC is equal to Vm by pi, VRMS is equal to Vm by 2. Just substitute here. You will get Vm square by Vm square by pi square whole divided by Vm square by 4. So Vm square will get cancelled. We will get eta is equal to 4 by pi square. That we will get 40.6% in terms of percentage. So this is the standard efficiency of half-wave rectifier. Now let us know what do you mean by form factor. Form factor is defined as ratio of, I am telling that ratio of RMS value divided by average value. My RMS value is what? Vm by 2. My average value is what? Vm by pi. So Vm will get cancelled. You will get pi by 2. That is equal to 1.57 something. This is my form factor. Now next, let us calculate what is the peak factor for half-wave rectifier. Peak factor is defined as the ratio of peak value divided by RMS value. Now my peak value is what? Vm. In the sinusoidal input waveform, this is my peak value. This is my input. This is my peak value. Positive peak value, negative peak value is minus Vm. My peak value is Vm. What is RMS value? Vm by 2. So Vm will get cancelled. Finally form factor will get 2. So these are the some consideration regarding half-wave rectifier, and keep in mind we will get tau is equal to 121%. Because of this reason only half-wave rectifier is technically cannot be useful for rectification process, AC to pulsating DC conversion. So this is all about regarding half-wave rectifier. Thank you.